Okay. So last lecture. Thanks to everyone for hanging in there that's here or online. So a couple of announcements. So there are some things I'm waiting on from the office for some room times. So when I get that information, I'm going to send out a couple of more emails. So far, I've only heard from 2 people about an alternative time due to exam conflicts, or whatever, scheduling. So if I don't hear from others by the end of the day, I've got to schedule that, and it's going to be much harder to accommodate people. So please let me know today. There will be a review, a Zoom review, and I'll send an announcement about that for the course on Monday at 6 p.m. Well, I mean, I'm planning for it to be an hour, but if it goes over, that's okay. And then, again, I'll send the link. It's the same link as the previous ones, but I'll send it again. I've gotten a lot of questions about what WB and S mean. I believe I know what they mean, but I don't want to say it until I double check that. So I will double check it, and I will send an announcement concerning that as well, and maybe clarify the list. So yeah, great. The finally, the SAC students, I will be sending an email about that as well, but we're still waiting on some room accommodation for that. Okay, if you have questions concerning the scheduling or whatnot that I didn't just mention or address, then let me know, and after class, and I'll see what I can do. Okay. So today, what we want to do is we want to talk about the last theorem, which fits into this general scheme of this Stokes theorem kind of template that we've been talking about. And for that, we need, again, to identify one term, actually, this time, before we had to talk about generalizing the type of integral, the type of domain we are integrating over, whether it's a vector or scalar and so on. We don't have to do that anymore. But we do need one more concept, and that's the concept of that derivative, that lowercase d, that appears in this generalized theorem, where we have something like this. So what we need to identify for this last version, which is the divergence theorem, is this derivative. And so for that, we need to say what divergence is of a vector field. So let me give the definition, and we'll do an example. So let's let F. And this divergence is something you can define in any dimension, but we'll talk about it in dimension 3. Divergence of a vector field. Then the divergence of F, this is just a scalar function, not a vector field, not like curl, but rather a scalar function, which is just the derivative of p with respect to x plus the derivative of q with respect to y plus the derivative of r with respect to z. Sort of a natural thing to consider, I guess. But okay, well, there it is. And it's very easy to compute, very easy to, as long as the functions aren't insane, it's a pretty easy thing. So there's other notation, just like with curl, another notation for this is we can take div f. It's the same notation, same definition as above, but you take it, you do this kind of thing. And again, you imagine this nabla operator as being sort of a vector with del x, del y, del z. Just sort of, in a sense, dot product. Okay. So let's see here. So we can take an example. Let's do a problem. Let's take a look. So let's say we have f would be 2 examples equaling x, y, z, or say g equaling minus y, x. So let's find their divergence. So div is divergence. Find their divergence. So solution. Okay, we just apply it. Div f here. Derivative of x is 1 plus 1 plus 1, so we get 3. On the other hand, the divergence of g is 0 plus 0 plus 0. Now, so the computation of this is very easy, not a hard thing to do, right? So what does this mean, though? What is the meaning of this notion of divergence? And for that, there's a very simple kind of interpretation of what divergence is telling you. So if you have a vector field, let me draw the two-dimensional version of these two vector fields. So let's just forget about that for a second. So F looks like this. It's pointing outward from the origin. And as we get larger, in other words, as we get farther from the origin, our vectors get longer, right? So we get very long. And on the other hand, for G, our vectors do get longer as we go out from the origin, but this, as you'll recall, we've seen this vector field before. This is rotational kind of vector field. It's like that. So what is divergence telling us? Well, if you think of this vector field as giving you the velocity of a fluid, okay, say on a table or something like that, divergence is, and say that fluid is what's known as like an incompressible fluid. So you can't it's not, the temperature is constant, it's not expanding or contracting. Divergence is telling us if we have sort of sources or sinks in our table. If that fluid is sort of flowing out at certain places, then our divergence gets negative. If somehow there's a faucet that's turned on that's bringing in extra water, then we have a positive divergence. It's giving us a scale function that's telling you how much is sort of being pushed in to that fluid, how much fluid is being pumped in or out. Does that make sense? This is the intuition behind it. Right, so we have this intuition of this new derivative, and of course it is a derivative. We see these partial derivatives appearing. So now we want a theorem that's relating this. So it's like our generalized Stokes theorem. So let's bring that down. And to sort of illustrate what's going on here, I want to kind of give this general picture, summarizing to some degree what we've done. So all of these theorems that we have, really, if you look at them, are concerning oriented domains, D. We use the scalar definitions to sort of define the vector definitions, but all of these have some sort of oriented domains involved. So let's make a list of our oriented domains. Okay, so we have a point. That's a domain that's oriented. If we think of it as an oriented domain, we'll think of it as having a sign plus or minus attached to it. We have a curve. We have a surface S. And we have this like a region. This we haven't talked about as much yet, but we can talk about a region, call it E, and it's going to be contained in 3 space. So if region is not something that makes sense, think of it as just a blob. So it has volume, is what we want to think of. You can think of it as an open set if you want, or a closed set with an open interior. Some kind of blob. Okay. So what is the dimension of our domain? Well, of course, for a point, it's 0. For a curve, it's 1. Surface is 2. And this blob, if I have volume, I want to think I have 3 dimensions. These domains are, I'm referring to are this domain D. All right, what is the integrand that we can actually calculate here? We're going to integrate something. Well, if we have a point P, it's true we could evaluate a vector field, but let's not. Let's just evaluate a scalar function. And as I said, most of these integrals that we're going to have, well, at least when we have a curve or a surface, we have these new notions of integrals, this vector curve and vector line integrals or vector surface. So here we'll have a vector field. Here we'll have a vector field. And here we'll have, well, if we have a region in R3, way back when we were first discussing integration, we talked about how to integrate scalar functions in those regions. I know it's been a while, but we did talk about it, and we know how to do it, at least in principle. So we can integrate scalar functions over these guys. So let's say we give ourselves some notation here. So what is a scalar function? Well, let's call it f, lowercase f. Okay. What is a vector field? We'll call it capital F. And here we'll also use capital F. Here we'll use lowercase f. This symbol here just means it's an element of the set of all of them. It's one of them. Now, how do we do the integrals? What are the integrals? Well, if we're going to integrate over a zero-dimensional space, and our point P is oriented, positive or negative, we just evaluate. This is our integral. And depending on the orientation of P, we either put a plus or a minus there. For a vector field over a curve, we know that we have a vector line integral. And the notation for that is this. And someone the other day came and asked me, how do I know whether it's a vector line integral or a scalar line integral? And again, you should look and see, the first thing to look for really is what's in here. If it's a vector field, you probably have a vector line integral. But also the notation will have an S here that's either got a vector over it or is bold. And that will indicate that it's a vector line integral. Similarly, if you want to integrate our vector field here, we'll also have a vector capital S over our surface S. And finally, if we want to integrate over a region E here, we just do an ordinary old triple integral over E of our function f of x, y, z dv. And I have notions of how to do all of these things. Now, all of this, as I said, tells us some things about what this generalized template looks like. So in particular, these oriented domains, these are this domain D or this boundary. We also have the integrand, which is eta. But one thing we're missing in this table here is this derivative, lowercase d. But in fact, we have it appearing, there we go. For a scalar function, we know how to go to a vector field, don't we? What's a derivative that takes us from a scalar function to a vector field? Gradient. Right? Gradient. Now, what's the derivative that takes us from a vector field to a vector field? Just learned it recently. Curl. Great. Or curl. And we just learned it very recently. A derivative that takes a vector field to a scalar function is divergence. Now, to each one of these arrows, each one of these derivatives, we have a theorem. One of these generalized Stokes theorems. The first theorem we have is the fundamental theorem of line integrals. And it reads like this. It says f of q minus f of p is equal to the integral over a curve C of the gradient of f dot ds. That's the theorem that goes in between these two. The theorem that goes in between these two we learned on Tuesday, Stokes theorem. And it tells us that an integral over a closed curve, which is a boundary of a surface of f dot ds, is equal to the double integral over the surface of, curl of f dot ds. It should be parentheses here. And today we have one more theorem, and that covers this derivative. And it relates a three-dimensional scalar integral, which is of a divergence of a vector field, with the vector integral of the vector field itself. So this is, I'll write it down and then say what it is. So this integral will look like this. So the boundary will be a closed surface. And we're going to take a vector integral f dot ds. This will equal the triple integral over a region E, which has boundary S, of the divergence. I'll use this notation just for consistency. Divergence of f dv. This last one is called the divergence theorem. And let's write it out more clearly. It's also known as Gauss's theorem. So let me write this out clearly, so we have everything we need. So first we want E to be a region in R3, and we want it to be oriented. We want it to be closed and bounded. So closed and bounded. With boundary equal to S. And this should be oriented away from E. So outwardly. Okay. And then the statement is just, so we have some extra conditions. We want the boundary not to be too horrible. It should be sort of smooth, or at least, smooth, except for maybe a dimension 1 part where it has some corners. But okay, I'm going to omit some of those details and just state the result, which is that we get this formula. And of course, here again, I also need to say some words about our vector field F being differentiable. But let's assume F is nice. I'm going to make all of those blanket assumptions. But I should probably say where F is differentiable in E. So it's defined, it's differentiable. Okay. So let's do a problem. Let's do a problem. See how this helps us. All right, so let's take S to be a sphere, radius 3. Centered at the origin. The origin. And oriented outward. Okay, and let F be the following vector field. This is vector field x minus y squared, xz plus y, xy minus c. Calculate following integral over S. Be a vector surface integral. And right when you see the vector surface integral, everyone starts tensing up, including myself, and feeling very worried, because what we've certainly learned, I think, over the last couple of lectures is that vector surface integrals can be quite a project, right? You have to, if you want to actually calculate them, you have to parametrize your surface, you have to calculate this compatibly oriented normal vector, and take dot products, and then, well, sometimes it turns out nicely, but even then, even when it does, it's often a lot of work. However, now we have this wonderful theorem. And we should use it. And as I'm trying to emphasize over and over again, these theorems are very practical, very useful things to have in your toolkit. And without them, some problems that are very difficult will stay difficult. But with them, they often become quite easy. So let's see. We notice, even though I didn't write it this way, this is the surface S, of course, is closed. And I want people to be comfortable with the idea. The double integral is the double integral. If I have a surface, it's a surface. Adding this thing when you have a closed surface is sort of optional. It emphasizes it's a closed surface, but you know, for closed surfaces, you don't need to write it. That's fine. Okay, and closed means there's no boundary. Just so people know what I mean by when I say closed surface. So like a sphere is a closed surface, there's no boundary to it. Whereas, you know, like a disk or some kind of, you know, not perfect disk has a boundary, that's not closed. All right, so let's apply the theorem. So note, S is the boundary of the ball of radius 3. So we have some region, let me call this ball B, radius 3. We have a region that gives us the surface S as its boundary, oriented compatibly. And so by, of course, F, we check and we look, and F is indeed defined on the ball and differentiable on the ball. So by the divergence theorem, we have the following equation. That the triple integral, the double integral of S of F dot ds, this is equal to this triple integral over our ball of the divergence of F dv. And who can tell me what the divergence of F is? 1. Great. 1. And who can tell me now what it means to integrate 1 over a 3-dimensional region? What are you going to get? In general, you're going to get what? The volume of that region. Integrate 1 over a region, you get the volume. And we know how to calculate the volume of the ball of radius 3. This is 4/3 pi r cubed is 3 cubed. Or 4 times 9 is 36 pi. And that's it. No parametrization of a sphere, no nasty computation, no calculating that cross product of t theta cross t phi, none of that. Okay. So now I want to spend the rest of the lecture today. We'll do another sort of computation, but I want to spend the rest of the lecture today kind of identifying some of the patterns we see here, because there are some patterns. And let's take a look. So what's something we know? If I look at this diagram up here, there's something actually that we know we learned about last time, which was that if I have a conservative vector field, first of all, what does it mean, conservative vector field? What it means is I'm in here, I'm a vector field, and I've come from some scalar function. In other words, I've taken a scalar function f and I've hit it with this gradient and I get a vector field. That's what it means to be conservative. It's the gradient of some scalar function. And what we learned last lecture was that if I had a conservative vector field and I took its curl, well, taking curl is in some ways like taking the cross partials condition. And the cross partials condition on a conservative vector field is 0. What that tells us is that if I compose these two operations, take the gradient and then the curl, I get 0. And the pattern is that we can do that again. The same applies here. The same applies here. If we start with a vector field and take the curl and then take the divergence, we get 0 again. So note, like the fact that the curl of the gradient equals 0, we also have that, the divergence of the curl of a vector field. This is something that's easily checked, but it has some consequences. It has some consequences. So the point is that these conservative vector fields enjoyed some very privileged properties. They were really, really wonderful. If we wanted to compute line integrals, in particular, of a conservative vector field, it became extremely easy. We had path independence. So we talked about path independence. F is conservative. We saw that the integral f dot ds over a curve is path independent, meaning it only depends on the endpoints. And in particular, one thing that implied was that if we had a closed curve and we took this again, this is when F is conservative, this closed line integral, this was 0. This is 0. Now, the same kind of thing can be said if we bump up a dimension. This pattern sort of continues, except the notion of being conservative is replaced with the notion of having a vector potential. So when F has a vector potential, what does that mean? That means that F is equal to the curl of some other vector field, capital A. Well, then what we saw was that the surface vector integral of F, saw this last time, where surface, this is sort of surface independent. In other words, it only depends on the curve boundary. And that gives us another notion that is easily seen from this, but you can also see in other ways, which is that if I take a closed integral of one of these solenoidal type fields, this is also called an incompressible field. Well, it is, if it has a vector potential, it is incompressible. So if I take a closed surface and I take this integral, this is 0 as well. So let's see, why is this true? I mean, there's a way of doing it where you sort of cut your surface up and you glue two pieces together and you show that you use Stokes' theorem. You can do it that way. But let's see why this is true with our new tool. So the reason, so one reason, although, so, okay. So one reason. So if S is the boundary, it's not always the case, but if it is the boundary of some region E and F, pardon me, F is defined on E. It's differentiable, meaning it's defined and differentiable on E. Then, E. Then what can we say? Well, we can use now the divergence theorem. Namely that this surface integral S, not ds, this is equal to the triple integral of the divergence of F. dV. But as I was just saying, we were noticing this pattern here, which is that in the case of the vector, conservative vector fields, we take the curl of a gradient, we get 0. But here, if I have a vector potential, in other words, F is the curl of A, here I'm taking the divergence of the curl of A. And we also have that that's 0. So this is the integral of 0 dV, which is 0. So this is showing why this is true. This is true, though, even if there is no, S is not the boundary of some region where F is differential. This is true more generally than that. We can use Stokes' theorem for that, but nonetheless. All right. So now, what I want to notice is we actually saw something fairly subtle that occurred, and it has a real physical reason it's occurring. before when we were considering Stokes, well, maybe not Stokes theorem, but Green's theorem, which is a version of Stokes theorem, and conservative vector fields. And I want to make the same kind of observation in the case of vector potentials in this context. So here's what we're going to do. So we're going to ask the following question. So given F, vector field F, does F have a vector potential if it passes the, okay, if div F, I'll just say this way, div F equals 0. So this is the pattern I want people to, okay, I know this is a lot. There's a lot of new ideas here, and I'm trying to put a lot of these things together. This is my only chance, my last chance. So let me explain what I'm trying to say here. There was some very big subtlety that went on previously. Let me go back to the diagram. And the subtlety concerned conservative vector fields that lived here. We had this test, cross partials test. And if we took our vector field F and we hit it with the cross partial test and we got 0, then we passed the cross partial test. And then there was a question, if it passes the cross partial test, is it the case that it's conservative? Does it come from some scalar function? The answer to that question was no, not generally. It's only true if this vector field was defined on a simply connected domain. And then it was yes. If it was not, then the answer was no. We spent some time seeing an example of that. It was a sort of rotational vector field that we saw. That rotational vector field actually comes from electromagnetism. Now we can also look at another vector field here and ask the same question. You can say, okay, let's suppose we have divergence 0. Does it come from, is it the curl of some other vector field? We know that if it is the curl, then when we hit it with divergence, we get 0. But is it true that if divergence of a vector field is 0, that it is the curl of something? Let's see. Let's see. Let's consider the following vector field. The vector field we've actually worked with. It's the following vector field. It's x over x plus y, x squared plus y squared plus z squared to the 3 halves. This is y over x squared plus y squared, z squared, halves, z. Let's consider this vector field. Same denominator in each case. Well, let's check the divergence. The divergence is going to be, okay, well, I have to take a derivative. So I'll take a derivative of the numerator with respect to x. So I'm taking derivative of this with respect to x, that's 1. But now I want to multiply by one copy of x squared plus y squared plus z squared. And then I'm going to subtract the derivative of the denominator and use the power rule. And so that the derivative of the denominator will be 2x times 3/2 x. So I get 3x. The same thing holds for y. I'll get x squared. Well, a similar thing, I should say, holds for y. We get minus 3y. Should be x squared, pardon me, 3y squared. X squared plus y squared. C squared to the 5/2. And here for z, a similar thing occurs. I get x squared plus y squared plus c squared. It's just the quotient rule, really. 3c squared over x squared. 5/2. And you can see we've got the same denominator in each case. So we get 3 copies of x squared plus y squared plus c squared, and we're subtracting 3x squared plus y squared plus c squared. So this whole thing is equal to 0. Awesome. So this passes our divergence test. We had a cross partials test before, let's call it a divergence test, and we can ask, does this have a vector potential? Is it the curl of some vector field? Well, one thing we just saw when we were talking about these patterns was that in this case, when I do have a vector potential, if I have a closed surface and I integrate over that closed surface, I get 0. So let's take a closed surface. Let's take a sphere. So given a sphere, radius r, centered at the origin, we can compute this double integral over S, let's call it S, oriented outwardly, of f dot ds. We did this computation. I did it 2 times. I did it by parametrizing the sphere, and then I gave you a way of doing it by just sort of realizing what the vector surface integral is and identifying the normal vectors. But actually I didn't do it. I did the half sphere, the upper hemisphere. But doing it over the entire sphere is really just twice the fun. You just get 2 times the result that I had last time. So look in your notes and you'll see that the result you get here, we did the upper part, we got 2 pi, we'll get 4 pi in this case. So check notes. Now, I don't know a lot about 4 pi, but I know it's not 0. It's not 0. So we're in a similar situation that we were in before when we were talking about conservative vector fields. We saw before that there were certain vector fields that passed the cross partials test. But when I integrated them over a closed curve, I got something non-zero. Now I have something that passes this divergence test, and when I integrate it over a closed surface, I get something not zero. So I do not have that this is the curl of some vector field. So there's no vector potential. This lands me in the same situation I was in before, which is I had this, there was some criteria I needed, and it wasn't about vector fields, and it wasn't about cross-partial conditions or divergence conditions. It was about the space that I was working on and the space of definition of my vector field. There's something intrinsic to that space. And I want to say, what could I do? So before, what we said is, okay, if we passed the cross-partial condition, or the cross-partial tests, if we pass this test here for f, and if f was defined on a simply connected region, then f was conservative. That's what we said before. I want a similar statement here. I want to say if I pass my divergence test here, and f is defined on some kind of region, then it will have a vector potential. So let me ask you guys, is f defined on a great region? Is it defined everywhere? Where is it not defined? The origin. F is not defined at the origin. So is F defined on a simply connected region? Question? Answer? How many did say yes? How many say no? Exactly 0 people were right. If I puncture 3 space at one point, it's still simply connected, right? We've got some cowboys here, right? If you want to like use your noose or whatever, I'm sorry, not, what do you call it? Lasso. What is, I don't know this stuff, guys. Cinch, I did learn about cinching. I told my wife about that. Yeah, so if you have a lasso, sorry, not noose, animal friendly here. If you have a lasso and you've got a puncture in your rodeo, like over somewhere, you know, it's not going to stop you from cinching that lasso, is it? It's just a point that's missing. You can still close up that curve. It's simply connected. You can puncture as many points as you want in 3 space if you're just puncturing a point. Now, if you took out a whole line of 3 space, then your lasso would have problems because you couldn't break through that line, you know, if you went around it. So this is simply connected, still simply connected. But there's another more abstract version of connectedness, to connectedness, which says if you were to play, well, be a rodeo, like a, I don't know what, a balloon rodeo man. If you can take, so what is this? There is another version of simply connected, which is to say to connected, which says that any surface can be contracted. Any surface, not just a loop, but a surface can be contracted. And I can't do that if I'm missing a point. If I throw a sphere around that point, I can't pull that sphere over that point without popping that bubble. That's there's a legitimate, rigorous mathematical way of saying that you cannot do that. But if you can always do that, if you can always collapse a surface, then indeed this test will tell you that you do have a vector potential. So then the theorem is, if F is defined, this is not in the book, but it's true, on a 2 connected region, and div F equals 0, then it has a vector potential. Okay, this won't be on the test, but I wanted to share it with you. It actually does have some pretty serious consequences in physics. I had a great time. Thanks everyone for all your effort. I will see you Monday evening, and good luck on your prep for the exam.